Venus and Earth are often seen as sisters in space, but their fates could not be more different. These two planets have a lot in common. They are similar in size, have rocky surfaces, and are located relatively close to each other in the solar system. At first glance, it seemed like they could have followed the same path, but that is far from the case. Earth is home to liquid water and life, while Venus has become a hot, dense, and inhospitable world. This huge difference between the two is one of the greatest mysteries in astronomy, and understanding why Venus took such a drastic turn could help us learn a lot about how planets evolve. So what makes Venus so different? It all comes down to its atmosphere. Venus's atmosphere is mostly made up of carbon dioxide, which is a powerful greenhouse gas. Because of this thick carbon dioxide-rich air, Venus traps heat like a blanket, preventing it from escaping back into space. This causes the surface temperature to soar to a scorching 460 degrees, hotter than even Mercury, the closest planet to the Sun. But it's not just the heat. The pressure on Venus is 90 times higher than it is on Earth. These harsh conditions are the result of processes that have gotten worse over time, and they make Venus one of the most extreme places in our solar system. However, it wasn't always like this. Climate models show that Venus may have had oceans of liquid water in its past. In fact, scientists believe these oceans could have lasted for hundreds of millions of years, creating a potentially habitable environment. So, what went wrong? The most likely reason is that Venus gradually became too hot. As the sun's heat intensified, Venus started losing hydrogen from its atmosphere, which set off a dangerous cycle. Without hydrogen, water vapor couldn't stay in the atmosphere, and instead carbon dioxide took over, trapping even more heat. This runaway greenhouse effect caused Venus to become the inhospitable world it is today. Another factor that played a big role in Venus's transformation is the lack of a magnetic field. On Earth, our magnetic field protects us from harmful solar winds, which can strip away lighter elements like hydrogen from the atmosphere. Venus, however, doesn't have this protection. This made it harder for Venus to hold on to the elements that are essential for maintaining a stable climate, like hydrogen and water. In contrast, Earth's magnetic field has been active for billions of years, which helped it maintain a stable environment capable of supporting life. Venus also has a strange rotation. It rotates extremely slowly, and in the opposite direction to most other planets, including Earth. In fact, a single day on Venus is longer than a year on the planet. This odd rotation impacts the planet's heat circulation, which has caused extreme weather patterns. Some scientists believe this slow and reversed rotation might be the result of a huge impact in Venus's distant past. An impact of that size could have tilted Venus's axis and changed its rotation, leading to the planet's unbalanced climate. Even though Venus doesn't have tectonic plates like Earth, there is clear evidence of geological activity. The planet's surface is covered with volcano-like formations, large flat domes, and signs of recent lava flows. Around 500 million years ago, Venus's surface appears to have undergone a process called resurfacing, which may have released massive amounts of gases into the atmosphere, further boosting the greenhouse effect. Since Venus lacks water and erosion, its surface has remained remarkably well preserved, making it difficult to get a clear picture of its distant past. Still, radar mapping from orbiting spacecraft like NASA's Magellan has helped scientists uncover the planet's geological history, revealing vast areas of Venus that are relatively young and still undergoing change. Despite the extreme conditions, Venus is not a completely dead planet. The Soviet Union's Venera missions, including the famous Venera 13, sent probes to Venus's surface to capture images and analyze the soil. However, these probes were destroyed by the intense heat and pressure, with most lasting only a few minutes. Still, they confirmed that Venus's surface is rocky and lifeless, but it also revealed that Venus isn't completely static. The planet's internal activity is still going on, and scientists are working hard to understand more about how its geology and atmosphere are changing. In 2020, scientists detected a molecule called phosphine in the clouds of Venus. On Earth, phosphine is linked to biological processes, leading to speculation that Venus could support microbial life in its clouds. This possibility has sparked a lot of excitement in the scientific community, though the discovery is still debated. Some researchers suggest that the phosphine could have been produced through non-biological means, so we're far from concluding that there's life on Venus. However, the presence of this molecule suggests that Venus's atmosphere has a complex and not fully understood chemistry, especially in a region around 50 to 60 kilometers above the surface where the pressure and temperature are similar to those on Earth. In this layer of Venus's atmosphere, conditions are extreme, but they are still less hostile than on the planet's surface. Scientists are considering sending balloons or probes to this region to study its atmosphere more closely. If there is life floating up there, it would be unlike anything we know, and studying it could open up entirely new possibilities for life in dense atmospheres and high temperatures. These kinds of investigations could also help scientists understand exoplanets that are very similar to Venus, with thick atmospheres and scorching temperatures. So how did Venus go from potentially being a world with oceans and a hospitable climate to becoming the toxic desert we see today? To answer this question, scientists need to study a lot of different areas, including geology, climate, atmospheric physics, and the dynamics of planetary orbits. Each new piece of information helps us build a better picture of how Venus evolved, and it also gives us valuable clues about how other planets in our solar system and beyond might develop. Venus is an ideal place to test climate models and simulate how planets with dense atmospheres and high temperatures behave. NASA and other space agencies have planned future missions to Venus, including NASA's Veritas and Da Vinci missions. These missions will map Venus's surface more precisely and study its atmosphere in much more detail. One of the key questions is whether Venus was ever truly habitable, and if so, for how long? These answers could help scientists better understand the conditions needed for habitability on exoplanets, especially those that are similar to Venus in size and atmosphere. Venus may be inhospitable today, but it still has a lot to teach us about planetary formation and evolution. In fact, studying Venus could help us better understand the Moon's origin, which is another big mystery in space science. The leading theory about the Moon's formation is called the giant impact hypothesis. This theory suggests that around 4.5 billion years ago, a Mars-sized object collided with Earth, sending a cloud of debris into space. Over time, this debris came together to form the Moon. This impact may have also affected Earth's tilt and rotation. However, this theory is not without its problems. When scientists analysed lunar rocks brought back by the Apollo missions, they found that the Moon and Earth have very similar chemical compositions, especially in terms of isotopes. This is unexpected if the Moon was formed from an impactor, since the classic model suggests the Moon would mostly be made of the impactor's material. To address this, some scientists have proposed that the impact was much more violent than previously thought, which would cause Earth's material to vaporize and mix with that of the impactor. This could have led to the Moon's composition being more similar to Earth's. Some computer simulations support this idea, showing that such an event is possible. There are other theories as well, like the idea that the Moon and Earth formed side by side from the same disk of dust. But this idea doesn't explain some key features of the Moon, like its composition and its angular momentum. Another possibility is that Earth captured the Moon's formation through gravitational forces, but this also has problems. Recent studies suggest that the Moon might not have formed in a single event, but rather through a series of smaller collisions. This idea, known as fragment accumulation, may better explain the Moon's mass distribution and internal composition. However, this theory is still in development, and it requires even more detailed simulations of the early solar system. The geology of the Moon also provides some important clues. Its crust is made up of a rock called a northocite, which is formed from a magma ocean. This suggests that the Moon was once completely molten after its formation, which fits with the idea of a massive collision. The absence of volatile elements like water also supports this theory, as such a high-energy event would have vaporized these elements. Differences in the Moon's core and its mass distribution also align with the impact hypothesis, as does the Moon's synchronous rotation, where one side always faces Earth. All of these factors, whether in Venus, the Moon, or any other planet, are pieces of the puzzle that scientists continue to work on. By studying Venus's strange and extreme conditions, We can not only learn about its own past, but also gain insights into other planets, moons, and even exoplanets that might share similar characteristics. The more we learn about Venus, the better we can understand the forces shaping planets throughout our solar system and beyond. The idea of a ninth planet beyond Neptune, often referred to as Planet 9, has been a topic of great interest in recent years. The hypothesis came about after scientists noticed strange gravitational effects on objects within the Kuiper belt, an area beyond Neptune that is home to icy bodies known as trans-Neptunian objects, TNOs. These TNOs follow unusual orbits that appear to be influenced by the presence of something massive, yet no such object has been directly observed. Planet 9 is thought to be a planet with a mass between 5 to 10 times that of Earth. This hypothetical planet is believed to orbit the Sun at a distance of hundreds of astronomical units, far beyond the orbit of Pluto. If it exists, it would have a very elliptical orbit, meaning it would take between 10,000 and 20,000 years to complete a single revolution around the Sun. However, its great distance from Earth makes it incredibly difficult to detect with current technology. Astronomers have observed that several TNOs share similar orbital characteristics, which is highly unlikely to be a coincidence. Computer simulations suggest that a planet of Planet 9's size and orbit could be responsible for the clustering of these objects over millions of years. Additionally, it could explain the tilted orbits of certain objects, such as the planetoid Sedna, which has an orbit almost perpendicular to the plane of the solar system. These anomalies are hard to explain using only the known planets in the solar system, which has led many scientists to believe that there may be a large unseen planet out there. There are two main theories about where Planet 9 might have come from. One suggests that it was captured from another star system during the early stages of the Sun's formation. Another theory proposes that it originally formed in the inner solar system and was then ejected to its current position through gravitational interactions with Jupiter or Saturn. Both theories are consistent with what we know about early planetary dynamics, but as of now there is no direct evidence to support either one. While the existence of Planet 9 is still hypothetical, there are alternative explanations for the observed phenomena. Some scientists believe that the apparent clustering of TNOs is a result of observational bias. Telescopes can only scan certain parts of the sky more effectively, so the apparent distribution of these objects might be skewed. Another possibility is that instead of a single massive planet, a collection of smaller objects could be responsible for the gravitational effects observed. Planet 9 could also explain some anomalies in the tilt of the Sun relative to the plane of the planets. Currently, the Sun's axis is tilted by about 6 degrees compared to the average orbital plane of the planets. A massive object at a great distance could have caused this tilt over billions of years. Although this is a secondary hypothesis, it adds weight to the argument that something else may be influencing the architecture of the outer solar system. The search for Planet 9 is being carried out using powerful telescopes designed to detect faint and slow-moving objects in the deep sky. Due to its long orbit, Planet 9 would move very slowly across the sky, making it difficult to distinguish from background stars. Even if the planet does exist, it could take years to spot it visually. As of now, no candidate has been confirmed. Astronomers are also observing the orbits of long-period comets from the Oort cloud, a distant region of the solar system, to see if there is any evidence linking their behavior to the presence of Planet 9. However, these clues are still being interpreted with caution, as the Oort cloud is too far away for direct observation, and its objects are widely scattered. Planet 9 differs from the concept of the Planet X that was proposed in the 20th century. Planet X was discarded after the discovery of Pluto and further adjustments to the masses of Uranus and Neptune. In contrast, Planet 9 is based on recent data and modern computer simulations, and it does not aim to explain past errors, but rather unexplained gravitational phenomena. This makes the theory more scientifically credible than the earlier Planet X hypothesis. If Planet 9 is confirmed, it would significantly change our understanding of the solar system. It would suggest that the solar system contains large bodies beyond the regions we have currently mapped. The discovery of Planet 9 could also force a revision of the definitions of what constitutes a planet, and could lead to a renewed interest in exploring the outer solar system. On the other hand, if Planet 9 is not found, astronomers will have to revisit the models used to interpret TNO data. This could involve refining statistical methods and developing new techniques for analysing orbits. In either case, the search for Planet 9 is pushing the boundaries of our knowledge and improving the tools available for studying distant objects. The search for a ninth planet also raises an important question. Are there artificial structures in our solar system? The idea that alien-made objects might exist on other planets or the moons has long intrigued scientists and the public. One of the most famous examples of this is the face on Mars photographed by the Viking 1 probe in 1976. In the original image, a rocky formation appeared to resemble a human face, which led to widespread speculation about ancient civilizations or extraterrestrial ruins on Mars. However, higher resolution images from later missions, such as Mars Global Surveyor and Mars Reconnaissance Orbiter, showed that the face was just a natural hill with specific shadows. This phenomenon is known as pareidolia, the brain's tendency to see familiar patterns in random shapes. Similar claims have been made about other supposed artificial structures on Mars, the Moon, and Saturn's moons. These include alleged pyramids on Mars, symmetrical structures on the Moon, and hexagonal formations on Saturn's moons. In every case, detailed analysis has shown that these formations are natural and consistent with known geological processes. Many of these discoveries were based on low-resolution images or subjective interpretations. While some people continue to believe in the existence of artificial structures on other worlds, planetary geology shows that natural processes like erosion, volcanic activity, and impacts can create complex shapes that might look like man-made objects. Despite this, there have been no confirmed discoveries of artificial structures anywhere in the solar system. Even claims of unusual anomalies in orbit or on the surface of celestial bodies have been explained by natural causes, such as gravitational interactions, rotation, or gas ejection. The search for artificial structures in the solar system is mostly speculative, and no scientific evidence has supported these claims. Actual artificial satellites, such as space probes and landers, are the only confirmed man-made objects in orbit. Any unusual behavior observed in objects like asteroids or comets can usually be attributed to their natural properties, such as gas ejection or unpredictable movement due to gravitational forces. Modern astrobiology focuses on the possibility of microbial life in extreme environments, but the idea of finding artificial structures remains outside the realm of evidence. Scientists use strict protocols to identify signs of life and technology beyond Earth. These include analyzing spectral data, environmental chemistry, and the organization of materials. So far, none of these tests have pointed to anything artificial in the solar system. Public interest in the idea of artificial structures has driven the use of artificial intelligence to analyze planetary images. Algorithms are trained to recognize unusual shapes and symmetries, which can be helpful for legitimate scientific purposes. These methods can identify natural features such as caves, tunnels, and other geological formations that may be relevant for future exploration. However, the use of AI in planetary image analysis must be done carefully to avoid biased interpretations. In the search for extraterrestrial intelligence, the SETI, Search for Extraterrestrial Intelligence, project focuses on detecting radio signals rather than looking for physical structures. The possibility of discovering alien technology through direct observation is considered extremely unlikely. Any object placed in the solar system by an alien civilization would have to survive for billions of years, or it would have to be placed very recently, something that contradicts the current data. The study of craters, terrain, and other features on planets like Mars and the Moon is now done with increasingly high-resolution imaging technology. This has allowed scientists to identify potential locations for future human missions, such as caves or lava tubes. However, no formations have been found that require an artificial explanation. All the patterns observed so far are consistent with natural geological processes. The idea of artificial structures on other planets is often explored in science fiction, but in the realm of real science, no evidence has been found to support the existence of alien technology in our solar system. While the search for life beyond Earth continues, it remains focused on detecting biological signatures rather than technological ones. If artificial structures do exist in the solar system, they remain beyond our current detection capabilities. For now, scientists continue their search for microbial life in extreme environments, but the idea of finding alien-built technology remains firmly in the realm of speculation. Enceladus, one of Saturn's moons, has captured the attention of scientists due to its surprising potential for habitability. Cassini, the spacecraft that explored Saturn and its moons, revealed incredible details about Enceladus, particularly its water plumes. These plumes are jets of water vapor, salts, and simple organic molecules, and they are ejected from cracks in the moon's icy crust. The presence of these substances suggests that water is interacting with rocks beneath the surface in a way similar to hydrothermal vents on Earth's ocean floor. This process, combined with the discovery of salts, points to a salty ocean beneath the surface, a significant finding that indicates a chemically active environment. The evidence gathered from Cassini's mapping of Enceladus's gravity shows a thick ice crust about 20 to 30 kilometers deep, beneath which is a global ocean. This ocean likely interacts with the moon's rocky core, creating the perfect environment for chemical reactions that could support life. Additionally, the jets of water come primarily from the moon's south pole, suggesting a heat source that is localized to that area. This heat is believed to come from tidal heating, a process in which Enceladus is flexed by gravitational forces from other Saturnian moons like Dione. This flexing heats the moon's interior, keeping water in a liquid state beneath the ice. Tidal heating is also thought to play a similar role in other moons like Europa, one of Jupiter's moons, which also has a subsurface ocean. However, what makes Enceladus particularly interesting is its ability to actively expel material into space, allowing scientists to study the composition of the ocean directly. The salts and silica found in the plumes are very similar to what we find in Earth's oceans, which strengthens the hypothesis that there may be hydrothermal vent systems on Enceladus. These systems are known to support unique ecosystems on Earth without the need for sunlight. If Enceladus has something similar, even simple life could exist, likely in the form of extremophiles, organisms that thrive in harsh conditions. One of the most intriguing findings from Enceladus's plumes is the detection of methane, a molecule that on Earth is often associated with biological activity. While methane can also be produced through chemical reactions between water, rock, and heat, its presence in high concentrations is suggestive of an ongoing and active process, possibly even biological. It's important to note that while this methane doesn't prove life, it does make the idea much more plausible. Further research into the structure of Enceladus's ocean is also ongoing. Some models suggest that the ocean may cover the entire moon, with greater chemical activity occurring in the southern hemisphere. This uneven distribution of heat and activity could either be the result of ancient tectonic fractures or varying internal heat sources. The thin ice crust in the polar regions of Enceladus allows material from the ocean to escape into space, which facilitates easier study of the ocean's composition. Despite its small size, only about 500 kilometers in diameter, Enceladus is one of the most fascinating objects in the solar system. The ongoing activity of the jets, which has been observed for over a decade, suggests that the internal system is stable. The expelled material from the moon also contributes to Saturn's E-ring, showing how Enceladus affects the broader system. This interaction between Enceladus and Saturn's rings is just one more example of how the moon influences its surroundings. Enceladus's ice crust acts as a protective barrier, insulating the ocean beneath from the vacuum of space. This insulation helps maintain stable conditions, such as pressure and temperature, within the ocean, allowing for the possibility of complex chemical reactions to occur over millions of years. Unlike other geologically active worlds, such as Earth, Enceladus gives scientists indirect access to what lies beneath its surface, making it one of the most accessible targets for studying potentially habitable environments outside of Earth. The organic compounds detected in the plumes of Enceladus are not complex, but their presence is still significant. These compounds include carbon, hydrogen, nitrogen, and oxygen, elements that are essential to life as we know it. While these compounds alone do not prove the existence of life, they do make Enceladus a chemically promising environment. When combined with liquid water, heat, and salts, these elements create the right conditions for life to potentially develop. Cassini wasn't specifically designed to detect life, but the evidence it gathered made Enceladus one of the most intriguing places in the solar system for astrobiology. While we don't yet know if Enceladus harbours life, its ocean, its interaction with its core, and the presence of organic molecules strongly suggest that it could be a suitable environment for life. Enceladus continues to be a top priority in the search for life beyond Earth. Moving from Enceladus to Mars, we look at another intriguing question in planetary science. Did Mars have oceans? Mars, the red planet, has long intrigued scientists because of its surface features, such as outflow channels and delta formations, which suggest that liquid water once flowed on the planet. For decades, these features have raised the possibility that Mars had rivers, lakes, and even oceans in its distant past. One of the most promising areas for the existence of ancient oceans on Mars is Vastus Borealis, a large basin in the northern hemisphere. This basin is thought to be the floor of an ancient ocean, and the terrain and morphology of the region support this idea. Some orbital data even shows possible shorelines and sedimentary deposits that resemble what we would expect to find around ancient coastlines. However, the debate is ongoing, as some scientists question whether these features are truly coastal or the result of other geological processes. Recent studies have found hydrated minerals on Mars, such as clays and sulfates, which can only form in the presence of liquid water under specific conditions of temperature and acidity. These minerals provide further evidence that liquid water may have existed on Mars for extended periods of time. In addition to this, Mars likely had an active hydrological cycle, precipitation, runoff, and infiltration, similar to Earth's cycle. This would mean that Mars once had significant bodies of surface water, such as lakes and seas, especially in low-lying regions. However, confirming the existence of ancient oceans on Mars is difficult because there is no continuous shoreline to serve as a clear marker. Some explanations propose that tectonic activity or freezing processes may have caused deformations to the landscape over time, making it difficult to identify clear coastlines. Another possibility is that the ocean was frozen, which would explain the lack of obvious shoreline features. More recently, evidence of ancient tsunamis has been found in regions of Vastus Borealis. These chaotic deposits could be the result of asteroid impacts that created massive waves in a shallow ocean, providing indirect evidence for a large body of water. Other evidence suggests that Mars had lakes that lasted long enough to accumulate fine layers of sediments. Some of these sediments are layered in a way that suggests they were formed by seasonal cycles, supporting the idea that liquid water existed on the planet for extended periods. While it is still unclear whether these lakes were connected to a larger ocean or were isolated, their presence strengthens the argument for a once watery Mars. Mars lost its oceans due to a combination of atmospheric loss and a collapsing magnetic field billions of years ago. Without a strong magnetic field, Mars was exposed to the solar wind, which caused its atmosphere to erode over time. As a result, much of the water on the surface evaporated, while some of it remained trapped as ice beneath the surface. Today, water on Mars exists only in the form of ice, and it can only be found in certain conditions, such as in the polar ice caps or in subsurface brines. Even though modern Mars doesn't have oceans, the evidence from its geological past suggests that the planet once had conditions capable of supporting life. Scientists are particularly interested in analysing ancient lake beds and sedimentary deposits, as these may contain chemical traces or even microscopic fossils that could reveal whether Mars supported life in the past. Understanding how Mars lost its oceans can provide valuable insights into how planets lose their habitability. The same process that turned Mars into a dry, barren world could help explain how other planets in the solar system and beyond may also become inhospitable. Lastly, we turn to Saturn's iconic rings. Saturn's rings are some of the most visually stunning features in the solar system, composed primarily of water ice with some rocky material. These rings stretch over 280,000 kilometers in diameter, but are only about 10 meters thick on average. Despite their beauty, the origin of Saturn's rings is still a mystery. One hypothesis suggests that the rings are the remnants of a moon that was torn apart by Saturn's powerful gravity. If a large icy satellite ventured too close to Saturn, tidal forces could have pulled it apart, creating the ring system we see today. Another theory is that the rings formed from leftover material that never coalesced into a moon during the early solar system. These particles of ice and rock could have remained in orbit around Saturn, forming a disk rather than a moon. This would mean that the rings are as old as Saturn itself. However, recent data from the Cassini spacecraft challenges this idea, suggesting that the rings may be much younger, perhaps only 100 to 200 million years old. This younger age hypothesis fits with the rings' bright, clean appearance, as older rings would likely be darker, due to accumulated dust and debris from micrometeorites. Cassini also observed waves and gaps in the rings, which are influenced by the gravitational pull of Saturn's moons. These waves and gaps, along with other features, show that the rings are active and constantly evolving. In conclusion, Saturn's rings are not just a beautiful mystery, but an active, evolving system shaped by both internal and external forces. Understanding their formation and age could provide important insights into the history of Saturn and the early solar system. Saturn's rings are some of the most iconic features in our solar system. They are composed mostly of water ice, with some dust and rocky material, and stretch over 280,000 kilometers in diameter, though they are only about 10 meters thick on average. Despite their beauty, the origin of Saturn's rings remains one of the biggest unsolved mysteries in planetary science. Several theories attempt to explain how the rings formed, with one suggesting that they are remnants of a moon torn apart by Saturn's gravity. If a large icy satellite ventured too close to Saturn, tidal forces could have broken it apart, spreading the debris into a disk. Over time, this material could have flattened out and formed the rings we see today. This theory is supported by the fact that Saturn's rings are primarily made of clean ice, which is consistent with the idea that they were formed from the breakup of a moon. Another hypothesis is that the rings formed from leftover material that never coalesced into a moon in the early solar system. Gravitational interactions with Saturn could have prevented clumps of ice and rock from forming a stable satellite, causing them to remain in orbit as a loose disk. According to this idea, the rings would be as old as Saturn itself, over 4 billion years. However, recent data from the Cassini spacecraft challenges this theory, suggesting that the rings might be much younger, perhaps only 100 to 200 million years old. If true, this would mean the rings formed well after Saturn's formation. The ring's brightness supports this theory, as older rings would likely be darker due to accumulated dust from micrometeorites. This younger age hypothesis leads us back to the disrupted moon theory, but with a more recent event. A moon-sized object might have collided with another body, or strayed too close to Saturn, breaking apart under gravitational stress. This would explain the youthful appearance and high purity of the ice particles in the rings. However, for this event to have happened recently in cosmic terms, it must have been rare and improbable. Cassini also detected fine variations in the ring structure, such as waves and gaps. Some of these features are caused by the gravitational pull of Saturn's moons, which act like shepherds shaping and maintaining the rings. Others may result from resonances or impacts. These dynamic processes show that the rings are active, constantly evolving, and not static relics from the early solar system. In terms of mass, Saturn's rings contain much less material than even a small moon. This means that over time they could dissipate due to micrometeoroid bombardment and gravitational spreading. Some scientists believe the rings may disappear entirely within the next 100 million years. Others suggest that ring systems may be temporary features that form and fade throughout a planet's life. If this is the case, Saturn's rings could be just one example of the transient nature of such systems in the universe. Spectroscopic analysis has also revealed differences in particle size and composition across different sections of the rings. Some areas contain clumps of ice meters across, while others are made of fine grains. The ring's colour varies slightly, possibly due to contamination from external sources. These variations provide clues about the ring's evolution and origin. Despite their mysterious and chaotic formation, Saturn's rings are highly organised. This balance between order and disruption adds to their allure. The structure of the rings is much more complex than the rings found around the other gas giants, like Jupiter, Uranus and Neptune. Saturn's rings are thicker, brighter, and more structured than those of its neighbours. This suggests that Saturn's rings might be either a special case or represent a phase that other planets went through and lost. Understanding these differences helps scientists model ring formation and planetary history across the solar system. The origin of Saturn's rings is still debated, but Cassini's data continues to refine our understanding. Each new layer of information reveals more about the forces that shape the rings. Whether Saturn's rings are young or old, formed from a moon or leftover debris, they remain a vivid reminder of the dynamic processes at work in our cosmic neighbourhood. Studying them allows us to learn more about the forces shaping planetary systems and how they evolve over time. Moving from Saturn to Jupiter, we now explore one of the most famous features in the solar system, Jupiter's Great Red Spot. This massive storm located in the southern hemisphere of Jupiter has been a part of the planet for at least 30 years. The Great Red Spot is an anticyclonic storm, meaning it rotates counterclockwise and has wind speeds of up to 430 km per hour. What makes it so fascinating is its longevity. Unlike hurricanes on Earth, which typically dissipate within days or weeks, the Great Red Spot has persisted for centuries. Its size, depth, and intense coloration have raised many questions, and its origins remain one of the biggest mysteries of planetary science. The storm's longevity is partly due to Jupiter's lack of a solid surface. Without land masses to disrupt atmospheric flow, Jupiter's weather systems can evolve freely over long periods of time. The exact cause of the storm's formation is still unknown, but it likely began as a large system of interacting vortices in Jupiter's turbulent atmosphere. Smaller storms may have merged over time to form a massive, stable vortex. Jupiter's powerful internal heat and rapid rotation contribute to the complexity of its weather patterns, creating alternating bands of eastward and westward winds that help sustain structures like the Great Red Spot. The position of the Great Red Spot between two jet streams is crucial to its longevity. These jets act as barriers, preventing the storm from drifting north or south. As a result, the storm remains locked in place, slowly changing shape and colour, but staying roughly in the same latitude. This stability has allowed the Great Red Spot to last far longer than any storms on Earth. However, it's not completely static. Its size, colour and intensity have all evolved over time. Historical records show that the storm has shrunk significantly in the last century. It was once over 40,000 kilometres wide, but now it measures less than 16,000 kilometres across. Its shape has also become more circular, and its colour has shifted from a deep red to more of an orange tone. Scientists are still trying to understand why these changes are happening, and some suggest that the storm might be losing energy and could eventually dissipate. The Great Red Spot extends deep into Jupiter's atmosphere, possibly as far as 300 kilometres down. Unlike Earth's weather systems, which are shallow and confined to the surface, the red spot is a three-dimensional vortex. This depth may help explain its extraordinary stability and its energy reservoir. One theory is that the Great Red Spot draws energy from smaller surrounding vortices. As it absorbs them, it replenishes its momentum and extends its lifespan. Observations have confirmed that such mergers have occurred in recent decades. However, it's unclear how long this process can continue without external inputs. Another mystery surrounding the Great Red Spot is its colour. The exact chemical makeup responsible for its reddish hue is still debated. It may involve complex compounds formed when solar ultraviolet light interacts with ammonia and other gases in Jupiter's atmosphere. These reactions could create chromophores, which are coloured molecules suspended in the upper atmosphere. Variations in colour may also reflect changes in altitude or composition over time. The Great Red Spot is more than just a fascinating weather feature. It influences the surrounding atmosphere in a number of ways. It creates gravity waves and disturbs nearby jet streams. In some cases, it even deflects or absorbs smaller storms that cross its path. These interactions make it a central feature of Jupiter's meteorology. Studying the Great Red Spot helps scientists understand fluid dynamics on a planetary scale and provides insights into the long-term behaviour of massive storms. To deepen our understanding of Jupiter's atmosphere, scientists also compare the Great Red Spot with other Jovian storms, such as Oval Ba or Red Junior. Oval Ba formed in 2000 from the merger of smaller white ovals and later turned red. This process is thought to be similar to the chemical reactions responsible for the Great Red Spot's colour. Observing both systems provides an opportunity to test models of storm behaviour, energy transfer and atmospheric chemistry. Despite its shrinking size, the Great Red Spot remains active and continues to fascinate astronomers. It embodies the power and scale of gas giant weather systems, which operate under very different conditions than those on Earth. Long-term monitoring of the storm reveals subtle changes in its shape, structure, and energy, bringing us closer to understanding the mechanisms that formed and sustained it. Lastly, we turn to the question of whether there is life in Europa's subsurface oceans. Europa, one of Jupiter's largest moons, has long been considered a promising candidate for extraterrestrial life. The surface of Europa is covered by a thick shell of ice, but beneath that lies a global ocean of liquid water. In fact, Europa's ocean is believed to contain more than twice the amount of water found on Earth. This ocean, combined with possible sources of heat and organic molecules, creates conditions that could support life. Magnetic field data from the Galileo spacecraft and surface features like chaotic terrain and ridges support the idea of a subsurface ocean beneath Europa's icy crust. Tidal forces from Jupiter cause Europa to experience constant gravitational stretching and squeezing, generating heat inside the moon and preventing the ocean from freezing solid. Unlike Earth, where sunlight keeps oceans liquid, Europa's ocean is maintained by internal energy, similar to what is seen on Saturn's moon Enceladus. Europa's ocean may even communicate with the surface through plumes of water vapor erupting from cracks in the ice. If these plumes are confirmed to be connected to the subsurface ocean, they could offer a way to study Europa's ocean without having to drill through the thick ice. The presence of salts and organic compounds on the surface further supports the idea that there is an ocean below, possibly in contact with a rocky seafloor. On Earth, similar environments where water meets rock are hotspots for microbial ecosystems. If life does exist on Europa, it would likely rely on chemosynthesis rather than photosynthesis, as there is no sunlight in the subsurface ocean. Microbes would draw energy from chemical reactions involving hydrogen and sulfur, similar to life near hydrothermal vents on Earth's ocean floors. Europa's ice shell, while thin, provides a protective barrier, shielding the ocean from Jupiter's intense radiation. This radiation could even contribute to surface chemistry by generating oxidants, which could then be transported down into the ocean, providing an energy source for life. Europa's ocean, if it exists, is dynamic and may support a thriving microbial ecosystem. However, the lack of direct sampling means we cannot confirm the presence of life yet. But the combination of liquid water, organic compounds, heat, and chemical processes makes Europa one of the most promising places in the solar system to search for extraterrestrial life. Europa, one of Jupiter's largest moons, continues to be a primary focus for astrobiological research. Scientists are particularly interested in its potential to support life, given the evidence for a subsurface ocean beneath its icy surface. This ocean may contain more than twice the amount of water found on Earth, creating an environment that could harbour life. The search for signs of life on Europa revolves around finding biosignatures, which are chemical or structural indicators of life. To achieve this, researchers are developing tools like plume sampling, seafloor imaging, and ice-penetrating radar to study the moon's ocean and its chemistry. Europa's potential to host life depends on a delicate balance of factors, including internal heat, chemical energy, and interactions between water and rock. These conditions make it one of the most compelling targets for astrobiology. Understanding Europa's ocean and its ability to sustain life in extreme conditions could provide insights into the nature of habitability on icy moons and exoplanets elsewhere in the universe. Uranus stands out in our solar system for its extreme axial tilt. Unlike most planets, which rotate with their axes perpendicular to their orbital planes, Uranus is tilted almost 98 degrees. This means the planet essentially rolls around the Sun on its side, with each of its poles experiencing 42 years of continuous daylight followed by 42 years of darkness. This unusual orientation has long puzzled scientists and raised important questions about Uranus's history. The most widely accepted explanation for Uranus's sideways rotation is a massive collision early in its history. A planet-sized object, possibly as large as Earth, is thought to have collided with Uranus at a glancing angle. The force of this impact would have been enough to tilt the planet's axis dramatically without destroying it. This theory also accounts for the unusual configuration of Uranus's moons, which orbit in a plane aligned with the planet's equator, further suggesting a violent event that reoriented the entire system. Some scientists propose that multiple smaller impacts over time could have gradually tilted Uranus. However, this doesn't fully explain the alignment of the moons, which points to a single catastrophic event. Another hypothesis suggests that gravitational forces from a massive protoplanetary disk during Uranus's formation could have gradually tilted the planet's axis. Though this idea is less violent, it would require very specific conditions to be plausible. Uranus's magnetic field adds complexity to its tilt. The field is highly tilted and offset from the planet's center, which could be a result of its unusual internal structure. This irregular magnetic field, along with the planet's tilted rings and moons, supports the impact hypothesis as the most likely cause of Uranus's extreme tilt. Jupiter is the largest planet in the solar system, but much about its interior remains a mystery. It is composed mostly of hydrogen and helium and lacks a solid surface, making direct study difficult. Understanding Jupiter's core is essential for modeling planetary formation and the evolution of gas giants. The traditional model suggests that Jupiter has a dense, rocky core surrounded by layers of metallic hydrogen and molecular hydrogen. The core would be several times more massive than Earth and composed of rock, ice, and heavy elements. However, recent data from the Juno spacecraft has painted a more complex picture. Gravity measurements suggest that Jupiter's core may not be compact and solid, but rather diffuse and extended. Instead of a sharp boundary, the heavy elements seem to be gradually mixed into the surrounding layers, challenging the traditional view of a neatly layered planet. One possible explanation for this diffuse core is a massive collision during Jupiter's early formation. A large protoplanet, perhaps 10 times the mass of Earth, may have struck Jupiter while it was still forming, disrupting its solid core and mixing heavy elements throughout its inner layers. This theory helps reconcile the observed gravitational field with models of Jupiter's internal structure and fits with the idea of chaotic conditions in the early solar system. Jupiter's overall density is relatively low, considering its mass, indicating the dominance of light gases in its structure. Despite this, the planet's gravitational influence suggests a concentration of heavier materials deep inside. By measuring variations in gravity, scientists can infer the planet's internal structure. These measurements, along with magnetic field observations, provide insight into Jupiter's deep interior. The planet's intense magnetic field, which originates deep within the planet, points to a large region of metallic hydrogen in motion. This dynamo effect is responsible for generating Jupiter's magnetic field and places constraints on the boundary between the metallic hydrogen layer and the core. While seismic data would be helpful to resolve these details, Jupiter's lack of a solid surface makes this impossible. Instead, scientists rely on gravity field analysis and magnetic field modeling as indirect methods for studying the planet's internal composition. Laboratory experiments simulating the extreme pressure and temperature conditions found inside Jupiter also provide important data, helping scientists refine their models. The presence of elements like oxygen, carbon, nitrogen, and sulfur in Jupiter's atmosphere gives clues about the planet's core composition. These elements are thought to be remnants of the planetesimals that Jupiter accreted during its formation. Their abundance supports the idea of a heavy element core, though whether these elements are concentrated at the center or distributed throughout the planet is still under investigation. Jupiter's core temperature is estimated to exceed 20,000 Kelvin, which creates extreme conditions under which hydrogen becomes metallic and other elements may separate into distinct layers. Understanding how materials behave under such pressures is crucial for interpreting Jupiter's structure and provides insight into the formation of gas giants and exoplanets. Jupiter's core also has implications for its satellite system. The planet's early mass and heat influenced the formation of its moons, with its gravitational field shaping their orbits and compositions. The core's heat may have also contributed to the evolution of moons like Europa and Ganymede, linking the planet's interior structure to the development of its moons. If Jupiter's core is indeed diffuse or eroded, it could have significant implications for other gas giants and exoplanets, helping scientists refine models of planetary formation and evolution in both our solar system and beyond. It suggests that core erosion and mixing may be common outcomes of giant impacts, which could explain the range of internal configurations observed in exoplanet data. Jupiter becomes a key test case for understanding how gas giants evolve internally. As Juno continues its extended mission, more detailed gravitational and magnetic data will help refine models. While we cannot yet directly see Jupiter's core, our understanding is advancing rapidly. Jupiter's interior remains a frontier of planetary science, revealing the complex interplay of gravity, chemistry, and extreme physics. Neptune, the farthest known planet from the Sun, receives very little solar energy yet emits significantly more heat than it absorbs. This energy imbalance has puzzled scientists for decades. Neptune radiates about 2.6 times more energy than it gets from sunlight. The source of this excess internal heat remains uncertain, especially when compared to its neighbour Uranus. Understanding Neptune's energy budget is crucial for decoding its internal structure and evolution. Several hypotheses have been proposed to explain Neptune's internal heat. One is that it retained more primordial heat from its formation. When planets form, they accumulate gravitational energy that gets converted into heat over time. Planets are expected to cool as this heat radiates into space, but Neptune may have cooled more slowly than expected, preserving some of that early energy. However, this alone doesn't fully explain the observed emission. Another possibility is ongoing heat production from the planet's interior. This could result from slow gravitational contraction, known as Kelvin-Helmholtz contraction, where the planet's mass compresses inward, releasing heat. Gas giants like Jupiter and Saturn also generate heat this way, so it's plausible for Neptune. Yet this process doesn't seem to operate in Uranus to the same extent despite their similar sizes and compositions. This difference remains a key mystery. Radiogenic decay has also been considered as a heat source. Elements like uranium and thorium release energy as they decay, heating a planet's interior. While this process is significant in rocky planets, its contribution in icy giants like Neptune is limited. The core of Neptune may contain some radioactive material, but likely not enough to explain the planet's energy output. This mechanism is thought to be secondary at most. Neptune's internal structure may hold the key to its unusual heat. The planet is thought to have a rocky core surrounded by layers of water, ammonia, and methane ices. These layers may allow efficient heat transport from the interior to the surface. If Neptune's materials are arranged in a way that avoids convection barriers, heat could escape more easily. In contrast, Uranus may have a stratified interior that traps heat, which could explain the thermal difference between the two planets. Some models suggest that Neptune's deep interior may be convectively active. Convective motion, the movement of warm material upward and cool material downward, can carry heat from the core to the surface. This process requires sufficient energy gradients and fluid mobility. If Neptune's interior supports this kind of mixing, it would maintain a consistent outward heat flow. Observations support the idea of active internal dynamics. Another factor may be Neptune's magnetic field. The planet's magnetic field is unusually tilted and offset from its center. This irregularity may reflect an internal structure where heat moves differently than in more symmetrical planets. While the connection between magnetism and heat transfer isn't fully understood, the correlation hints at a deeper relationship. Internal asymmetry may enhance thermal flux. Neptune also experiences extreme weather, with the fastest winds in the solar system up to 200 km per hour. These atmospheric dynamics may be influenced by internal heat flux. Rising heat could drive convection cells and jet streams, fueling the planet's storm systems. The most famous of these was the Great Dark Spot, a massive storm observed by Voyager 2 in 1989. While the storm has since vanished, similar features reappear frequently. The persistence of storms and temperature variations suggests active energy exchange between Neptune's interior and atmosphere. The source of this energy must be internal, given the low solar input. High-resolution infrared observations show that Neptune's heat is not evenly distributed. This unevenness provides clues about how and where the heat escapes. It also indicates that Neptune's atmosphere is deeply influenced by its internal state. Some scientists have proposed exotic mechanisms, such as phase separation of helium or superionic water layers. These ideas involve high-pressure physics that could release heat under extreme conditions. However, these remain speculative and require more data to validate. Laboratory experiments simulating Neptune-like pressures are ongoing and may help test these complex scenarios. The mystery of Neptune's heat has broader implications. If internal heat retention or release is sensitive to structure, other exoplanets could behave similarly. Studying Neptune helps refine models of ice giant formation and energy dynamics. These models are essential for interpreting the wide variety of exoplanets found to date. Neptune, as the best observed ice giant, serves as a benchmark. Despite many theories, the exact reason Neptune emits so much heat remains unresolved. Continued study of its structure, composition, and atmospheric behavior may provide answers. As new telescopes and missions gather better data, our understanding of Neptune's energy puzzle will improve. For now, the planet stands as a cold blue enigma with a hot interior. When the New Horizons spacecraft flew by Pluto in 2015, it dramatically changed our understanding of this distant world. Before the mission, Pluto was considered a cold, inactive, frozen rock at the edge of the solar system. But the images and data revealed a surprisingly complex and varied surface: mountains, glaciers, plains, and potential cryovolcanoes, suggesting that Pluto is geologically active. This was unexpected for such a small icy body so far from the Sun. One of the most striking features observed is Sputnik Planitia, a vast nitrogen ice plain shaped like a heart. This region shows no signs of impact craters, implying that it is relatively young geologically speaking. The surface appears to be constantly renewing itself, likely due to convective activity beneath the ice. The presence of large cells and polygonal patterns supports this idea, indicating that Pluto's interior is still active even though it is far from the Sun. Unlike rocky planets, Pluto's geologic activity doesn't come from plate tectonics or volcanic eruptions of molten rock. Instead, it is driven by the slow flow and deformation of ices like nitrogen, methane, and carbon monoxide. These ices behave like glaciers, shifting and evolving over time, even at extremely low temperatures. This is called cryogeology, geology driven by ice rather than rock. Another sign of activity is the presence of what may be cryovolcanoes. Features such as Reitmons and Peerymons resemble volcanic structures, but are composed of ice, not rock. These mountains have large central depressions, suggesting the possibility of past eruptions of water or ammonia-rich slush. If confirmed, cryovolcanism would imply the presence of internal heat sources beneath Pluto's surface. Tectonic features on Pluto also point to internal forces at work. Long faults and fractures, some stretching hundreds of kilometers, suggest that Pluto's crust has expanded. This may mean that a subsurface ocean, if it once existed, is now freezing and expanding. As water freezes, it increases in volume, pushing the surface outward. The existence of such fractures indicates global-scale structural changes. Gravity data from New Horizons hints at a possible subsurface ocean. The basin of Sputnik Planitia aligns with this idea. It may be sitting atop a denser subsurface layer. Some models suggest that beneath Pluto's crust lies a liquid water ocean, possibly mixed with ammonia. This antifreeze would keep the ocean from freezing entirely. If true, it would explain ongoing tectonic activity and surface renewal. Pluto's thin atmosphere also interacts with its surface. It is composed mainly of nitrogen, with traces of methane and carbon monoxide. Seasonal temperature changes can cause gases to freeze onto the surface or sublimate into the atmosphere. This cycle may contribute to the redistribution of ices across Pluto's surface, resulting in a constantly changing landscape. Even without strong winds or precipitation, surface color variations also point to complex chemistry and slow geologic processes. Dark regions like Cthulhu Macula contain tholins, organic compounds formed by solar and cosmic radiation. These molecules are created when ultraviolet light breaks down methane in the atmosphere. Over time, they settle on the surface and build up dark reddish patches. Their distribution may be influenced by surface activity and local conditions. Despite Pluto's small size and extreme cold, its interior may still retain enough heat to drive geologic processes. This heat could be slowly escaping through the crust, allowing the icy surface to deform and evolve. The slow pace of these changes makes them hard to detect in real time, but the lack of craters in many regions indicates active resurfacing. Pluto is far from a frozen fossil, as ongoing activity continues to shape its surface, making it one of the more intriguing bodies in our solar system. The variation in terrain on Pluto suggests a layered history, with some regions appearing ancient, heavily cratered, and seemingly untouched for eons, while others look fresh and relatively young, indicating recent resurfacing. This patchwork of ages reveals a world that has undergone dramatic changes over time, and suggests localized geological processes operating differently across Pluto's surface. Given Pluto's distance from the Sun, missions to it are rare, with New Horizons providing only a brief flyby. Despite this, the information gathered was enough to overturn old assumptions about Pluto being a geologically inactive rock, instead revealing an active, evolving world with surprising complexity. Its geology is still being interpreted through the data collected, but many questions remain. The evidence strongly supports the idea that Pluto is geologically active, with glaciers, fault lines, and possible cryovolcanoes. Its surface remains dynamic despite the extreme environment, and continued analysis will refine our understanding of this fascinating dwarf planet. Titan, Saturn's largest moon, is one of the most Earth-like bodies in the solar system, not in temperature or composition, but in surface processes. Titan has rivers, lakes, and even rain, though instead of water, these features are made of liquid methane and ethane. Titan has a thick atmosphere with weather patterns and seasonal changes, suggesting it has a functioning climate system with long-term cycles. Titan's atmosphere is mainly nitrogen, like Earth's, with small amounts of methane, which behaves similarly to water on Earth. It cycles between vapor, clouds, and precipitation. Rain falls onto Titan's surface, carving channels and filling lakes, and evaporation completes the methane cycle. These processes indicate that Titan has an active climate despite its cold temperatures. The Cassini spacecraft observed many of these features during its mission, and infrared and radar imaging revealed vast lakes and seas near Titan's poles. These bodies of liquid methane are not evenly distributed. Most are concentrated in the northern hemisphere, a distribution that may be tied to seasonal variations. Titan's orbit around the Sun takes about 29 Earth years, leading to long seasons. During southern summer, Cassini observed clouds and precipitation in the southern hemisphere, and as seasons changed, cloud activity shifted northward. This migration of weather patterns suggests a global climate system, with lake levels fluctuating over time. Liquid may evaporate in one hemisphere and accumulate in the other, forming the basis of a climate cycle. Wind patterns also play a role in Titan's climate. Dunes near the equator suggest persistent wind activity shaping the landscape. These dunes are made of hydrocarbon particles, not sand, and their orientation reveals wind direction over time. Seasonal winds may transport methane, shaping Titan's surface. Although sunlight is weak on Titan, it is still enough to drive photochemical reactions in the upper atmosphere. These reactions produce a thick haze of organic particles that varies with altitude and season. This haze influences surface temperatures by trapping heat and altering energy balance, with seasonal changes in haze thickness affecting how sunlight reaches the surface. The temperature variation between the poles and equator is less extreme than on Earth, thanks to Titan's dense atmosphere, but seasonal shifts still influence evaporation and precipitation rates. During winter, methane clouds and fog are more common near the poles, while in summer, evaporation dominates, clearing the skies. This seasonal shift creates a feedback loop in the methane cycle. Titan's lakes and seas are key indicators of climate dynamics, with shoreline changes over time hinting at fluctuations in liquid levels. Some features resemble dry lake beds, suggesting that liquid methane once filled these areas, but has since evaporated or migrated. This fluctuation could be driven by seasonal cycles, orbital variations, or longer-term climate patterns, similar to Earth's ice ages. Cloud activity varies from year to year, and sudden storms appear, spanning hundreds of kilometers. These weather events are tied to seasonal heating and contribute to erosion, sediment transport, and landscape reshaping. Cassini detected rainfall and wet streaks on the surface, confirming that precipitation does reach the ground. Though rare, these events support the methane cycle and validate climate model predictions. Titan's atmosphere must be replenished with methane over time, which suggests subsurface reservoirs or cryovolcanic sources that resupply methane lost to space. Without replenishment, Titan's atmosphere would deplete over geologic timescales. This replenishment adds a long-term layer to the climate cycle, connecting Titan's interior and surface systems. All evidence supports the existence of a methane-based climate cycle on Titan, from lake migration and storm activity to haze variation and seasonal weather shifts. Titan's atmosphere behaves in Earth-like ways, and its climate system is a rich area for continued study. This offers valuable insights into atmospheric systems beyond our planet. Ganymede, the largest moon in the solar system, is another fascinating world with a complex internal structure. It is even larger than Mercury and has a differentiated interior, meaning it has distinct layers, including a crust, mantle, and core. One of the most intriguing discoveries is the likely presence of a subsurface ocean beneath its icy crust, adding Ganymede to the list of potentially habitable worlds. Magnetic field measurements were key to uncovering Ganymede's internal structure. The Galileo spacecraft detected a magnetic field intrinsic to the Moon, which was unexpected. Even more interesting, it found evidence of a secondary magnetic field induced by Jupiter's own magnetosphere. This induced field suggests a conductive layer beneath the surface, most likely a salty liquid ocean. Models of Ganymede's interior estimate that the crust is between 50 and 200 kilometers thick, with a possible liquid water layer beneath it, about 100 kilometers deep. Below this lies a rocky mantle and an iron-rich core. The presence of a core capable of generating a magnetic field indicates that Ganymede underwent differentiation early in its history. This internal activity may have helped retain enough heat for the subsurface ocean to persist. Unlike Europa or Enceladus, where oceans are likely in contact with rock, Ganymede's situation may be more complex. Some models suggest multiple layers of ice and water, possibly with high-pressure ice separating the ocean from the rocky mantle. If true, this would limit chemical interaction between rock and water, which is important for potential habitability. However, other studies propose that brine water, with salts and ammonia, may prevent full freezing at deeper layers. This could allow some regions of the ocean to remain in contact with rock, at least intermittently. Salts also enhance conductivity, supporting the induced magnetic field data. The exact configuration of Ganymede's interior remains debated, and more data are needed to determine the thickness and extent of each layer. Surface features also provide clues about Ganymede's internal structure. It has both bright grooved terrain and darker, older regions. The bright areas are believed to have formed through tectonic stretching of the icy crust, possibly driven by subsurface movement related to ocean dynamics. Faulting and resurfacing processes indicate past or ongoing geological activity linked to internal heat. The presence of polar caps and frost patterns suggests cryovolcanic processes may have occurred in the past. Some regions show evidence of icy flows, potentially connected to upwelling material from below. While no direct observation of geysers or plumes, like those on Enceladus, has been made, surface morphology hints at complex internal processes. These processes may bring materials from the ocean closer to the surface. Ganymede's magnetic field is unique among moons and provides insight into its interior. A convecting liquid iron core is the likely source, similar to Earth's dynamo. This suggests that Ganymede's interior remains at least partially molten, and residual heat could help maintain the subsurface ocean, driving tectonic or cryovolcanic activity. Ganymede also shows evidence of ice tectonics. The grooved terrain appears to have formed by extension and cracking of the icy crust, requiring internal stress likely caused by thermal gradients or orbital forces. While less geologically active than Europa, Ganymede still reveals signs of internal motion. These processes shape its surface and suggest long-term internal evolution. The possibility of subsurface habitability depends on several factors, including the ocean's depth, composition, and whether it contacts the rocky mantle. If life exists there, it would likely be microbial and rely on chemosynthesis, similar to life near hydrothermal vents on Earth. Confirming this requires more detailed exploration of Ganymede's interior, and future missions may clarify these questions. The lack of a magnetic field on Mars further exposed the planet to long-term stripping of its atmosphere. Over time, various factors work together to deplete Mars's atmosphere, including solar wind stripping, thermal escape, and chemical weathering. Carbon dioxide in the atmosphere can react with minerals in Martian rocks to form carbonates, which lock CO2 into solid form. This chemical weathering process reduces the amount of CO2 in the atmosphere. While it is slower than other mechanisms, it has a significant cumulative effect over geologic timescales. This may help explain the relatively low levels of CO2 on Mars today. Mars still has a thin atmosphere, and seasonal variations occur. During winter, carbon dioxide freezes at the poles, lowering atmospheric pressure, while in spring it sublimates back into gas, increasing pressure again. However, these fluctuations are minor compared to the thick atmosphere Mars once had. Modern conditions on Mars are too cold and have too low of a pressure to support stable liquid water on the surface. Traces of the ancient atmosphere remain trapped in Martian rocks and meteorites, and measurements of isotope ratios, especially noble gases like argon, provide clues about the planet's atmospheric loss. Lighter isotopes escape more readily, and their depletion indicates how long the escape processes have been at work. These measurements align with models of long-term atmospheric erosion, confirming that Mars has been losing atmosphere for billions of years. Understanding how Mars lost its atmosphere also helps inform studies of habitability. A thicker atmosphere could have allowed stable liquid water and supported microbial life. As the atmosphere thinned, surface conditions became more hostile. If life ever emerged on Mars, it may have retreated underground, where pressure and temperature are more stable. Mars's climate history is deeply tied to its potential for life. The loss of the atmosphere through a combination of solar wind stripping, thermal escape, impact erosion, and chemical interactions sealed the fate of the planet. Studying this process provides valuable insights not only into Mars' past, but also into the atmospheric evolution of rocky planets. The asteroid belt, located between Mars and Jupiter, has long been thought to contain only dry, rocky bodies. However, recent years have brought discoveries that challenge this notion. Astronomers have identified objects in the belt that exhibit comet-like activity. These bodies, known as main belt comets or active asteroids, challenge the traditional distinction between comets and asteroids. They follow asteroid-like orbits but sometimes develop tails and comas, features typical of comets. The first recognized main belt comet, 133P Elst-Pizarro, was discovered in 1996. It follows a stable asteroid-like orbit, but showed a clear dust tail, a hallmark of cometary activity. Since then, more than a dozen similar objects have been found, including 238P, 324P, and 313P. These main belt comets' orbits lie entirely within the asteroid belt, ruling out the possibility that they are recent visitors from the outer solar system. This suggests that ice can exist much closer to the Sun than previously assumed. The key feature of these objects is their ability to release material into space, creating dust trails. Unlike traditional comets, which are primarily composed of ice from the Kuiper belt or Oort cloud, the activity in main belt comets may be triggered by localized sublimation, collisions, or rotational spin-up. In some cases, sunlight reaches subsurface ice, causing it to vaporize and carry dust outward, producing faint tails similar to classical comets. Evidence for sublimation as the cause of activity comes from repeated outbursts. Some main belt comets become active at the same point in their orbit, year after year, suggesting that solar heating drives the activity rather than collisions. However, impacts can still expose fresh ice by breaking the insulating surface layer. Once exposed, ice can begin sublimating, producing dust clouds. Another mechanism involves rotational instability. As sunlight hits an asteroid, it can create uneven thermal radiation, known as the Yarkovsky effect. Over time, this can change the object's spin rate. If the rotation becomes too fast, surface material may be ejected, creating transient dust trails. This behavior has been observed in objects like 3L11P Van Ness, which showed multiple tails likely caused by spin-induced shedding. Spectral analysis of some active asteroids indicates hydration or traces of volatiles. These findings support the idea that water ice may still exist beneath the surface. This challenges earlier assumptions that the inner solar system is completely dry. Instead, icy material may be preserved in the main belt, particularly in the outer regions, where temperatures are lower. The existence of main belt comets has significant implications for planetary science. It supports the theory that water and volatiles could have been delivered to early Earth by asteroid-like bodies. These objects may have played a significant role in transporting key ingredients for life, bridging the gap between rocky asteroids and icy comets. Studying active asteroids also helps refine models of solar system evolution. It shows that small bodies can undergo surface renewal even at relatively close distances to the Sun. The main belt may not be as static and inert as once thought. Instead, it hosts a diverse population of objects with dynamic histories and internal complexity. Main belt comets tend to be relatively small, typically only a few kilometers across, and their activity is weaker than that of traditional comets. As a result, they are difficult to detect, especially without dedicated surveys. However, new observation campaigns, including those using space-based telescopes, continue to find more candidates. As detection methods improve, more active asteroids are likely to be discovered. These objects provide a valuable laboratory for studying the transition between rocky and icy bodies, some of which may be ancient remnants of water-rich planetesimals that never formed into planets. In conclusion, yes, there are active comets in the asteroid belt. These main belt comets display comet-like behavior despite their asteroid-like orbits. Their activity is driven by sublimation, impacts, or rotational effects. These objects challenge the traditional classification of small bodies and offer important insights into the history of water in the inner solar system. The solar system doesn't have a solid edge like a wall or border, but scientists define its boundary using physical and observational criteria. One of the most widely accepted definitions involves the heliosphere, the bubble-like region of space dominated by the Sun's solar wind. The outer boundary of the heliosphere is called the heliopause, where the solar wind's pressure balances against the interstellar medium, effectively marking the end of the Sun's direct influence. Beyond the heliopause lies interstellar space, where particles and fields are no longer shaped by the Sun. The heliopause is not a fixed distance. Its location varies depending on solar activity and interstellar pressure. On average, it is about 20 astronomical units, AU, from the Sun, with 1 AU being the distance from Earth to the Sun. Both Voyager 1 and Voyager 2 spacecraft crossed the heliopause, confirming its existence through changes in particle and magnetic field data. Before reaching the heliopause, spacecraft passed through the termination shock, where the solar wind slows abruptly from supersonic to subsonic speeds. This region, called the heliosheath, is a turbulent zone filled with compressed plasma and magnetic fields. It acts as a buffer between the inner solar system and the interstellar medium. The distances to these regions are not the same in all directions because the heliosphere is asymmetrical. Even beyond the heliopause, the Sun's gravity continues to exert influence. Objects like comets in the Oort cloud remain gravitationally bound to the solar system. The Oort cloud is a theoretical shell of icy bodies that may extend up to 100,000 AU from the Sun. While it lies far beyond the heliosphere, it is still considered part of the solar system in a gravitational sense. The outer edge of the Oort cloud may represent the true gravitational boundary of the solar system. Another concept of a boundary is the Hill sphere, the region where the Sun's gravity dominates over that of other stars. The Hill sphere of the Sun extends out to roughly 1 to 2 light-years. Beyond this region, passing stars or galactic tides can disturb comets and other distant objects. So while the heliopause marks the end of the Sun's magnetic and particle influence, the gravitational boundary is much farther. Cosmic rays, high-energy particles from outside the solar system, also interact with these boundary regions. The heliosphere acts as a shield, deflecting or slowing many of these particles before they reach the inner planets. As spacecraft leave the heliosphere, they detect increased levels of cosmic radiation. These measurements help define the structure of this transition zone and improve models of space weather. Radio signals and plasma waves provide another way to detect the boundary. After Voyager 1 crossed the heliopause, it recorded changes in plasma density, confirming it had entered a new environment. The heliopause is not a permanent structure. Its size and shape vary over the 11-year solar cycle. When solar activity is high, the solar wind is stronger, pushing the boundary outward. During solar minimum, the heliopause can contract. This dynamic behavior makes it more like a fluctuating membrane than a rigid edge. Its movement affects how the solar system interacts with interstellar space. There are also boundary regions closer in, such as the bow shock or bow wave, the area in front of the heliosphere as it moves through the galaxy. There is ongoing debate over whether the heliosphere forms a classic bow shock or a gentler wave due to the relatively slow speed of the Sun's motion. These features mark how the solar system carves its path through the interstellar medium. For practical purposes, astronomers define the solar system's operational boundary at the heliopause. This is where the solar influence, in terms of particles and magnetic fields, effectively ends. However, depending on the context, whether gravitational, dynamical, or particle-based, different boundaries may apply. Each boundary offers a unique perspective on where the solar system ends. So yes, there is an invisible boundary, but it depends on what kind of limit is being discussed: solar wind, gravity, or orbital mechanics. The heliopause is currently the most direct and measurable marker, yet the solar system stretches far beyond it in terms of gravitational and orbital influence. In summary, the solar system has no single sharp edge but multiple layered boundaries. These include the heliopause, the edge of the Oort cloud, and the Sun's Hill sphere. Each defines a different kind of transition into interstellar space. At first glance, the solar system appears stable and orderly, with the planets following predictable paths around the Sun. However, when examined over very long timescales, gravitational interactions introduce complexity and potential chaos. While short-term orbits are stable, the long-term behavior of the solar system is not perfectly predictable. Small perturbations can compound over millions of years. The solar system is governed by Newtonian and relativistic gravitational laws, which allow scientists to model planetary motions with high precision for thousands or even millions of years. But the system is chaotic in the mathematical sense, extremely sensitive to initial conditions. Over hundreds of millions of years, small uncertainties can grow and lead to significantly different outcomes. This is known as dynamical chaos. One of the main sources of instability is gravitational resonance. When two or more planets have orbital periods in a simple ratio like 2:1 or 3:2, their gravitational tugs can accumulate. While some resonances are stabilizing, others can increase orbital eccentricity or inclination. Jupiter and Saturn, for example, are near a 5.2 resonance, which can subtly affect the orbits of other planets over time. Numerical simulations of planetary dynamics show that inner planets, especially Mercury, are the most vulnerable to long-term instability. Mercury's orbit is already elongated, and it is affected by both Jupiter's and Venus's gravity. In some extreme simulations, Mercury's orbit becomes so eccentric that it could collide with Venus or fall into the Sun. However, the probability of this happening is relatively low, estimated at about 1% over the next 5 billion years. The outer planets, Jupiter, Saturn, Uranus and Neptune, are more stable due to their large masses and wide spacing. Their orbits may shift slightly, but significant destabilization is unlikely on practical timescales. Still, even small changes in the outer solar system could cascade inward, affecting asteroid belts, comets, or even Earth. Planetary migration and resonance crossings in the past likely caused shifts in the solar system's configuration. The asteroid belt is one of the most chaotic regions in the solar system. Many asteroids reside in unstable zones due to resonances with Jupiter. Over time, these interactions can eject asteroids from the belt or send them into Earth-crossing orbits. Similarly, comets from the outer solar system can be perturbed by passing stars or galactic tides, sending them inward or ejecting them entirely. Earth's orbit is relatively stable, but it is not immune to variations. Its eccentricity, tilt, and axial precession change over tens of thousands of years due to gravitational influences. These variations drive Milankovitch cycles, which affect Earth's climate over geological timescales. While not threatening in a stability sense, they show how planetary dynamics influence habitability. Another source of potential instability is the cumulative effect of tiny perturbations, including those from general relativity. For example, the precession of Mercury's orbit was one of the first confirmations of Einstein's theory. These effects are small but measurable, and over billions of years they contribute to the evolution of orbital paths. Such subtle forces help refine models of long-term solar system dynamics. Stellar encounters are another factor. As the Sun orbits the centre of the Milky Way, it occasionally passes near other stars. A close stellar flyby could disturb the Oort cloud or even shift planetary orbits slightly. While rare, such events are not impossible. Over billions of years, cumulative effects from passing stars could influence the solar system's overall configuration. Despite all this, catastrophic instability, like planets being ejected or colliding, is statistically unlikely in the short to medium term. Current models suggest the inner solar system will remain mostly intact for at least 1 billion years. Major disruptions, if they occur, are likely to happen on timescales longer than the Sun's remaining main sequence lifetime. Still, the solar system is not a perfectly closed, unchanging system. Its stability is relative and depends on the timescale considered. On human and even civilizational scales, it is stable. On billion-year timescales, the potential for dynamical shifts and reconfigurations increases. These ideas help scientists understand planetary systems in general. In conclusion, the solar system is mostly stable in the near term, but it exhibits signs of long-term dynamical complexity. Small gravitational effects compounded over vast timescales mean that its ultimate configuration remains unpredictable beyond a certain point. Planetary magnetic fields are generated by a process known as the dynamo effect. This occurs when a planet has a liquid, electrically conductive layer, typically molten metal, that rotates and convects within the planet's interior. As these conductive fluids move, they create electric currents, which in turn generate magnetic fields. The motion must be sustained and organized to maintain a global field. This dynamo mechanism explains the magnetic fields of planets like Earth, Jupiter, and Saturn. For a magnetic dynamo to operate, 3 main conditions are required: a rotating body, a fluid conductor, and sufficient internal heat to drive convection. Earth meets these conditions with its molten iron outer core. The heat comes from both radioactive decay and residual formation energy. As the core cools, convection continues to stir the fluid iron, generating Earth's magnetic field. This field protects our atmosphere from solar wind and helps guide compasses. Other planets with magnetic fields follow the same basic principle but differ in composition. Jupiter and Saturn generate magnetic fields from metallic hydrogen, a phase of hydrogen formed under immense pressure. Uranus and Neptune also have magnetic fields, but theirs are tilted and offset, likely due to thinner or layered conductive regions. These ice giants may use slushy, salty water ammonia mixtures instead of molten metals as dynamos. Mars, on the other hand, no longer has a global magnetic field. Data from orbiters and landers indicate that Mars once had an active dynamo, but it shut down billions of years ago. Evidence comes from ancient Martian rocks that retain magnetic signatures, showing that a magnetic field once existed. The loss of this magnetic field left Mars vulnerable to atmospheric stripping by solar wind, contributing to its current thin atmosphere. The main reason a planet loses its magnetic field is thermal evolution. If a planet cools too much, convection in the core slows or stops. Without motion, the electric currents cease and the magnetic field fades. This likely happened to Mars, whose smaller size meant it lost internal heat faster than Earth. The core may have solidified, or convection may have become too sluggish to sustain the dynamo. The Moon also lacks a magnetic field today, but shows evidence of one in the past. Lunar rocks brought back by Apollo missions are magnetized, suggesting that a magnetic field existed over 3 billion years ago. The Moon's smaller size and limited internal heating likely caused its dynamo to stop early. The cause of its ancient dynamo is still debated, with some theories involving tidal heating or crystallization of the core. Mercury presents a unique case. It has a weak but active magnetic field despite its small size and slow rotation. Its field is offset and asymmetrical, hinting at unusual core dynamics. One theory suggests that part of Mercury's iron core remains molten, with convection driven by sulfur-rich layers or a stratified core. Despite being weak, Mercury's field is strong enough to interact with the solar wind. In gas giants, the magnetic fields are much stronger than Earth's. Jupiter's, for example, is 20,000 times more powerful. These strong fields shape vast magnetospheres that influence nearby moons and trap charged particles. These interactions produce phenomena like auroras on both the planets and their satellites. The sheer scale of these magnetic environments makes them important features of the outer solar system. When magnetic fields are present, they act as shields against solar radiation and wind, helping retain atmospheres and reduce surface radiation. Planets without strong fields, like Mars and Venus, are more exposed to space weather. Over long time scales, this can influence surface evolution, atmospheric chemistry, and potential habitability. Dynamo models continue to evolve with new data. Simulations combine fluid dynamics, thermodynamics, and magnetohydrodynamics to better understand planetary interiors. Each planet's magnetic behavior provides clues about its structure, thermal history, and evolution. Future missions, such as orbiters with magnetometers or seismology landers, will refine our understanding of planetary magnetic fields. In summary, planetary magnetic fields are created by convecting conductive layers deep within planets. Their formation and disappearance depend on internal heat, composition, and motion. These features mark how the solar system carves its path through the interstellar medium. For practical purposes, astronomers define the solar system's operational boundary at the heliopause. This is where the solar influence, in terms of particles and magnetic fields, effectively ends. However, depending on the context, whether gravitational, dynamical, or particle bosons, different boundaries may apply. Each boundary offers a unique perspective on where the solar system ends. So yes, there is an invisible boundary, but it depends on what kind of limit is being discussed: solar wind, gravity, or orbital mechanics. The heliopause is currently the most direct and measurable marker, yet the solar system stretches far beyond it in terms of gravitational and orbital influence. In summary, the solar system has no single sharp edge but multiple layered boundaries. These include the heliopause, the edge of the Oort cloud, and the Sun's Hill sphere. Each defines a different kind of transition into interstellar space. At first glance, the solar system appears stable and orderly, with the planets following predictable paths around the Sun. However, when examined over very long timescales, gravitational interactions introduce complexity and potential chaos. While short-term orbits are stable, the long-term behavior of the solar system is not perfectly predictable. Small perturbations can compound over millions of years. The solar system is governed by Newtonian and relativistic gravitational laws, which allow scientists to model planetary motions with high precision for thousands or even millions of years. But the system is chaotic in the mathematical sense, extremely sensitive to initial conditions. Over hundreds of millions of years, small uncertainties can grow and lead to significantly different outcomes. This is known as dynamical chaos. One of the main sources of instability is gravitational resonance. When two or more planets have orbital periods in a simple ratio like 2:1 or 3:2, their gravitational tugs can accumulate. While some resonances are stabilizing, others can increase orbital eccentricity or inclination. Jupiter and Saturn, for example, are near a 5.2 resonance, which can subtly affect the orbits of other planets over time. Numerical simulations of planetary dynamics show that inner planets, especially Mercury, are the most vulnerable to long-term instability. Mercury's orbit is already elongated, and it is affected by both Jupiter's and Venus's gravity. In some extreme simulations, Mercury's orbit becomes so eccentric that it could collide with Venus or fall into the Sun. However, the probability of this happening is relatively low, estimated at about 1% over the next 5 billion years. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are more stable due to their large masses and wide spacing. Their orbits may shift slightly, but significant destabilization is unlikely on practical timescales. Still, even small changes in the outer solar system could cascade inward, affecting asteroid belts, comets, or even Earth. Planetary migration and resonance crossings in the past likely caused shifts in the solar system's configuration. The asteroid belt is one of the most chaotic regions in the solar system. Many asteroids reside in unstable zones due to resonances with Jupiter. Over time, these interactions can eject asteroids from the belt or send them into Earth-crossing orbits. Similarly, comets from the outer solar system can be perturbed by passing stars or galactic tides, sending them inward or ejecting them entirely. Earth's orbit is relatively stable, but it is not immune to variations. its eccentricity, tilt, and axial precession change over tens of thousands of years due to gravitational influences. These variations drive Milankovitch cycles, which affect Earth's climate over geological timescales. While not threatening in a stability sense, they show how planetary dynamics influence habitability. Another source of potential instability is the cumulative effect of tiny perturbations, including those from general relativity. For example, the precession of Mercury's orbit was one of the first confirmations of Einstein's theory. These effects are small but measurable, and over billions of years they contribute to the evolution of orbital paths. Such subtle forces help refine models of long-term solar system dynamics. Stellar encounters are another factor. As the Sun orbits the centre of the Milky Way, it occasionally passes near other stars. A close stellar flyby could disturb the Oort cloud or even shift planetary orbits slightly. While rare, such events are not impossible. Over billions of years, cumulative effects from passing stars could influence the solar system's overall configuration. Despite all this, catastrophic instability, like planets being ejected or colliding, is statistically unlikely in the short to medium term. Current models suggest the inner solar system will remain mostly intact for at least 1 billion years. Major disruptions, if they occur, are likely to happen on timescales longer than the Sun's remaining main sequence lifetime. Still, the solar system is not a perfectly closed, unchanging system. Its stability is relative and depends on the timescale considered. On human and even civilizational scales, it is stable. On billion-year timescales, the potential for dynamical shifts and reconfigurations increases. These ideas help scientists understand planetary systems in general. In conclusion, the solar system is mostly stable in the near term, but it exhibits signs of long-term dynamical complexity. Small gravitational effects compounded over vast timescales mean that its ultimate configuration remains unpredictable beyond a certain point. Planetary magnetic fields are generated by a process known as the dynamo effect. This occurs when a planet has a liquid, electrically conductive layer, typically molten metal, that rotates and convects within the planet's interior. As these conductive fluids move, they create electric currents, which in turn generate magnetic fields. The motion must be sustained and organized to maintain a global field. This dynamo mechanism explains the magnetic fields of planets like Earth, Jupiter, and Saturn. For a magnetic dynamo to operate, 3 main conditions are required: a rotating body, a fluid conductor, and sufficient internal heat to drive convection. Earth meets these conditions with its molten iron outer core. The heat comes from both radioactive decay and residual formation energy. As the core cools, convection continues to stir the fluid iron, generating Earth's magnetic field. This field protects our atmosphere from solar wind and helps guide compasses. Other planets with magnetic fields follow the same basic principle but differ in composition. Jupiter and Saturn generate magnetic fields from metallic hydrogen, a phase of hydrogen formed under immense pressure. Uranus and Neptune also have magnetic fields, but theirs are tilted and offset, likely due to thinner or layered conductive regions. These ice giants may use slushy, salty water-ammonia mixtures instead of molten metals as dynamos. Mars, on the other hand, no longer has a global magnetic field. Data from orbiters and landers indicate that Mars once had an active dynamo, but it shut down billions of years ago. Evidence comes from ancient Martian rocks that retain magnetic signatures, showing that a magnetic field once existed. The loss of this magnetic field left Mars vulnerable to atmospheric stripping by solar wind, contributing to its current thin atmosphere. The main reason a planet loses its magnetic field is thermal evolution. If a planet cools too much, convection in the core slows or stops. Without motion, the electric currents cease and the magnetic field fades. This likely happened to Mars, whose smaller size meant it lost internal heat faster than Earth. The core may have solidified, or convection may have become too sluggish to sustain the dynamo. The Moon also lacks a magnetic field today, but shows evidence of one in the past. Lunar rocks brought back by Apollo missions are magnetized, suggesting that a magnetic field existed over 3 billion years ago. The Moon's smaller size and limited internal heating likely caused its dynamo to stop early. The cause of its ancient dynamo is still debated, with some theories involving tidal heating or crystallization of the core. Mercury presents a unique case. It has a weak but active magnetic field despite its small size and slow rotation. Its field is offset and asymmetrical, hinting at unusual core dynamics. One theory suggests that part of Mercury's iron core remains molten, with convection driven by sulfur-rich layers or a stratified core. Despite being weak, Mercury's field is strong enough to interact with the solar wind. In gas giants, the magnetic fields are much stronger than Earth's. Jupiter's, for example, is 20,000 times more powerful. These strong fields shape vast magnetospheres that influence nearby moons and trap charged particles. These interactions produce phenomena like auroras on both the planets and their satellites. The sheer scale of these magnetic environments makes them important features of the outer solar system. When magnetic fields are present, they act as shields against solar radiation and wind, helping retain atmospheres and reduce surface radiation. Planets without strong fields, like Mars and Venus, are more exposed to space weather. Over long time scales, this can influence surface evolution, atmospheric chemistry, and potential habitability. Dynamo models continue to evolve with new data. Simulations combine fluid dynamics, thermodynamics, and magnetohydrodynamics to better understand planetary interiors. Each planet's magnetic behavior provides clues about its structure, thermal history, and evolution. Future missions, such as orbiters with magnetometers or seismology landers, will refine our understanding of planetary magnetic fields. In summary, planetary magnetic fields are created by convecting conductive layers deep within planets. Their formation and disappearance depend on internal heat, composition, and motion. These fields shape planetary environments and offer insights into a planet's deep interior. What are Kuiper Belt objects? The Kuiper Belt is a vast region of icy bodies beyond the orbit of Neptune, stretching roughly from 30 to 50 astronomical units AU from the Sun. It is similar in structure to the asteroid belt but far larger and composed mostly of frozen volatiles like methane, ammonia, and water. The objects found here are known as Kuiper Belt objects, KBOs, and are remnants from the early solar system. They preserve the primordial material that formed the outer planets. The most famous KBO is Pluto, which was reclassified as a dwarf planet in 2006 when astronomers recognized it as part of a much larger population. Other notable KBOs include Iris, Maki, Maki, and Haumea, which are similar in size to Pluto. These large KBOs are sometimes called Plutos. Many smaller KBOs remain undiscovered due to their small size and great distance from Earth. They are cold, dark, and move slowly across the sky. KBOs are classified into different types based on their orbits. Classical KBOs, or Kinos, have relatively stable, near-circular orbits and are not strongly influenced by Neptune. Resonant KBOs like Pluto are locked in gravitational resonances with Neptune, typically in a 2:3 ratio. This means Pluto completes 2 orbits for every 3 of Neptune's, preventing close encounters. Scattered disk objects, in contrast, have highly eccentric orbits and were likely flung outward by Neptune's migration. These orbital classes offer clues to the early solar system structure. The distribution of KBOs reflects the migration of the giant planets, particularly Neptune. As Neptune moved outward, it disturbed nearby icy bodies, scattering some and capturing others into resonant orbits. This reshuffling helped create the Kuiper Belt's current structure. Many KBOs are believed to be leftovers from the planet formation era. KBOs are mostly composed of ice and rock, and many are covered in dark organic compounds called tholins. These form when ultraviolet radiation or cosmic rays strike simple molecules like methane and nitrogen. Over time, these compounds coat the surfaces with a reddish-brown colour. Spectral analysis reveals surface ices such as methane, water, nitrogen, and sometimes carbon monoxide. Some KBOs have moons and a few are part of binary systems. Pluto and its moon Charon are the best known example, with Charon being large enough to form a near double planet system. These binary KBOs are important for estimating mass and density, which help infer internal composition. They also reveal how collisions and gravitational interactions shape the region. Because they're so distant, KBOs are extremely cold, with surface temperatures near 40 to 60 Kelvin, 230 joules. This frigid environment has preserved their structure for billions of years. Unlike planets and moons closer to the Sun, KBOs have undergone little heating or geological processing. They serve as frozen time capsules, containing material in a nearly original state from the solar system's formation. The discovery of KBOs revolutionized planetary science. Before 1992, Pluto was thought to be unique. The discovery of additional KBOs showed that Pluto is just one of many large icy bodies. This led to the redefinition of what constitutes a planet and introduced the concept of dwarf planets. The Kuiper Belt is now recognized as a crucial part of the solar system. KBOs are also linked to short-period comets, which originate in the Kuiper Belt or nearby scattered disk. These comets occasionally get nudged into the inner solar system by gravitational interactions. As they approach the Sun, their ices vaporize and form tails. Comets like Halley's, which return every few decades or centuries, are thought to come from this region. The Kuiper Belt should not be confused with the Oort cloud, which is a far-distant spherical shell of icy bodies. The Oort cloud may extend up to 100,000 AU, while the Kuiper Belt lies just beyond Neptune. Both regions contain ancient icy remnants, but they differ in structure, origin, and behavior. The Kuiper Belt is disc-shaped and better studied. Missions like New Horizons have transformed our understanding of KBOs. After its flyby of Pluto in 2015, New Horizons visited another KBO, Arakoth, in 2019. This object, with its contact binary shape, revealed clues about how small bodies merged in the early solar system. Future missions may target other KBOs for flybys or sample returns. In summary, KBOs are icy, distant remnants from the early solar system. Their compositions, orbits, and distributions preserve a record of planetary migration and formation. Studying KBOs helps scientists piece together the history of our cosmic neighborhood. The outer solar system remains one of the least explored regions, leading scientists to wonder whether there could be one or more undiscovered planets beyond Pluto. The idea gained attention with visual observations of trans-Neptunian objects, TNOs, whose orbits appear clustered in unusual ways. This behavior is hard to explain unless something massive is influencing their motion. The leading hypothesis is the existence of a Planet 9. Planet 9 is a theoretical planet estimated to be 5 to 10 times the mass of Earth. It would orbit the Sun at a distance of 400 to 800 AU or more, far beyond the Kuiper Belt. Its gravitational pull could explain why certain TNOs like Sedna and 2012 VP113 have elongated, aligned orbits. These bodies seem to avoid close approaches to the Sun, suggesting an external perturber is shaping their paths. Computer simulations support this idea. When Planet 9 is added to models of the solar system, the clustering of distant objects becomes more coherent. The planet's orbit would likely be highly elliptical and take thousands of years to complete. It would be too faint and slow-moving to have been spotted by current telescopes, especially if it lies near its most distant point from the Sun. No direct observations have confirmed Planet 9's existence. Efforts to locate it include wide-field surveys with powerful telescopes, such as Subaru in Hawaii, and the upcoming Vera Rubin Observatory. These telescopes scan large sections of the sky looking for slowly moving objects. Detection is difficult due to its expected faintness and the vastness of the search area. There are alternative explanations for the observed orbital clustering. Some scientists argue that selection bias or small number statistics could exaggerate the alignment. Others propose that the cumulative gravitational influence of many small distant bodies, not a single large one, could produce similar effects. These ideas challenge the need for a ninth planet, although none have yet fully replaced the Planet 9 hypothesis. Additionally, astronomers continue to discover new TNOs with unusual orbits. Some of them do not fit neatly into any model, fueling further speculation. One example is the dwarf planet Sedna, which has a perihelion far beyond Neptune's influence. Its orbit raises questions about what forces placed it there, possibly a distant planet or a passing star in the early history of the solar system. Some hypotheses even suggest primordial black holes or rogue planets as explanations, though these are considered highly speculative. Such objects would be incredibly difficult to detect but would still exert gravitational influence. These ideas are part of broader efforts to explain unusual outer solar system dynamics using both conventional and exotic physics. Historically, the search for unseen planets has had mixed results. The prediction of Neptune based on Uranus's orbit was a success, but the search for Planet X led to false leads, including Pluto, which turned out to be too small. Planet 9, if it exists, would be the first major planet discovered since Neptune in 1846. Its discovery would reshape our understanding of the solar system's architecture. The outer solar system is home to many other structures, such as the scattered disk and the Oort cloud. These regions contain objects that may be influenced by bodies we haven't yet observed. If a planet does exist in these distant zones, it may affect not only TNOs, but also the influx of long-period comets into the inner solar system. Whether or not Planet 9 is real, its hypothesized presence has revitalized interest in deep sky surveys. It also highlights how much we still don't know about the solar system's outer frontier. The possibility of missing planets reflects the challenges of studying distant dim objects against the background of space. In the coming years, new telescopes will dramatically increase our ability to scan the sky. If Planet 9 exists, it is likely to be detected by 2030. Until then, it remains a strong, though unproven, explanation for orbital anomalies beyond Neptune. The mystery continues to drive both observational and theoretical research. In summary, there may be one or more planets beyond Pluto, but none have been confirmed. The Planet 9 hypothesis remains a leading explanation for observed orbital patterns in the outer solar system. Earth is unique among the rocky planets in that it has active plate tectonics. Large pieces of its outer shell, the lithosphere, constantly move, collide and recycle. This process shapes continents, drives earthquakes, and volcanism, and helps regulate the planet's climate. No other planet currently shows clear evidence of plate tectonics in action. Understanding why Earth alone exhibits this process requires looking at several key factors. One reason is Earth's internal heat. The slow churning motion of semi-solid rock in the mantle drives mantle convection, which exerts forces on the lithosphere, causing it to break into plates. Earth's size and composition allow it to retain enough heat to maintain this convective activity over billions of years. Without this heat, the engine of plate tectonics would stall. Another crucial factor is the presence of liquid water. Water acts as a lubricant for subduction, the process where one plate slides beneath another. It weakens minerals in the lithosphere and lowers melting temperatures, thus allowing the crust to deform and recycle. No other planet has surface or subsurface water in sufficient quantity or at the right conditions to support this mechanism. Water may be essential for sustaining tectonic motion. Earth's lithosphere is also divided into relatively thin and rigid plates that rest atop the softer asthenosphere. This mechanical layering allows the plates to move independently. In contrast, planets like Mars and Venus have thicker, more stagnant lithospheres that do not appear to break into distinct moving segments. Their surfaces show evidence of volcanic and tectonic features, but not plate boundaries or recycling. Venus presents an especially interesting comparison. Its surface is geologically young, suggesting episodes of resurfacing. However, it lacks features typical of plate tectonics, such as mid-ocean ridges or subduction zones. One theory is that Venus undergoes episodic overturn, a periodic planet-wide resurfacing event rather than continuous tectonic cycling. Its slow rotation and dry crust may prevent sustained tectonic activity. Mars shows signs of ancient tectonic stresses, including large fault systems and volcanic provinces. However, its smaller size led to faster cooling, likely freezing its tectonic processes early in its history. Without sufficient internal heat or a lubricated mantle, Mars' lithosphere became too rigid to break into plates. As a result, tectonic motion ceased long ago. The Moon and Mercury also show little to no tectonic activity today. Their small sizes mean they cooled rapidly and lack the internal energy to drive convection. Surface features like scarps on Mercury are likely remnants of global contraction rather than tectonic plate motion. These bodies demonstrate the role of planetary size in sustaining geological activity over time. Many moons, like Europa and Enceladus, exhibit ice tectonics, where frozen crustal plates shift and interact. While this resembles Earth-like tectonics, it occurs in icy shells over liquid oceans, driven by tidal forces rather than mantle convection. These icy worlds offer analogues but operate under entirely different mechanisms and materials. Tectonics also influences Earth's carbon cycle, helping stabilize climate over geological timescales. Subduction recycles carbon-rich rocks into the mantle, while volcanic eruptions release CO2 back into the atmosphere. This feedback loop helps maintain temperatures suitable for life. Without tectonics, carbon may accumulate on the surface or become permanently locked away, destabilizing the climate. The presence of a large moon may also contribute indirectly. The moon's gravitational pull affects Earth's rotation and internal dynamics, possibly aiding in heat distribution and core convection. However, this effect is debated and likely secondary compared to heat and water availability. Still, Earth's specific combination of conditions may be uniquely favourable. Many of these features are interconnected. A large, warm planet with abundant water, proper mechanical layering, and active mantle convection seems necessary for plate tectonics. Earth may be the only planet in our system where all these conditions align. That doesn't mean tectonics is impossible elsewhere, but it may be rare and difficult to maintain. In summary, Earth's active plate tectonics result from a combination of internal heat, liquid water, mechanical layering, and planetary size. These features make Earth unique among rocky planets in the solar system and other inner planets. The intense bombardment likely contributed to the formation of the Moon's large craters and may have played a role in the early evolution of Earth's atmosphere and oceans. The impacts could have delivered essential water and organic molecules, which are critical for the development of life. The late heavy bombardment also serves as a reminder of the chaotic early stages of our solar system's formation, where gravitational interactions among the planets, particularly Jupiter and Saturn, played a key role in shaping the environment we see today. The migration of these massive gas giants likely caused the redistribution of debris in the solar system, throwing icy bodies from the Kuiper Belt and Oort cloud into the inner solar system. This reshuffling would have contributed significantly to the spike in impacts during the LHB period. Understanding the LHB also sheds light on the frequency and scale of asteroid and comet impacts throughout the solar system's history. The bombardment had a lasting impact on the surface of planets and moons, creating an archaeological record that we can still study today. The study of impact craters on the Moon, Mars, Mercury, and other bodies provides valuable insights into the solar system's early dynamics and the processes that influence planetary formation. In summary, the late heavy bombardment likely resulted from the migration of Jupiter and Saturn, causing a destabilization of the solar system's smaller bodies. This period of intense impacts shaped the inner solar system and had long-lasting effects on planetary surfaces, including Earth. As we continue to study the geological evidence from planetary bodies, we gain a clearer understanding of the early solar system and its chaotic, dynamic processes, which likely reshaped the Moon system around Neptune. Triton's retrograde orbit and its unusual characteristics suggest that it was not originally formed in place, but instead was captured from the outer solar system, likely from the Kuiper Belt. This capture may have been a cataclysmic event, with Triton being snatched by Neptune's gravity during a close encounter, which also possibly disrupted or destroyed Neptune's earlier moons. Triton's relatively circular orbit, unusual for a captured object, suggests that it underwent a period of orbital circularization. This process likely occurred due to tidal interactions with Neptune, which slowly brought its orbit into a more stable configuration. Such a dynamic event would have made Triton's current orbit highly stable and prevented it from either crashing into Neptune or escaping its gravitational pull. The Moon's icy surface and geologically active features such as nitrogen geysers and a lack of impact craters further suggest that Triton has undergone resurfacing, possibly driven by internal heat from tidal forces. This ongoing geological activity supports the idea of Triton being a captured body, potentially from the Kuiper Belt similar to Pluto or other dwarf planets. Neptune's other moons, particularly the smaller irregular ones like Nereid, Halimeid, and S2004N1, further suggest a tumultuous past. Their eccentric, inclined and retrograde orbits point to more capture events, possibly from bodies in the Kuiper belt or scattered across the outer solar system. These moons' odd orbits contrast sharply with Neptune's regular moons, which typically have circular orbits within the planet's equatorial plane. The inner regular moons of Neptune, such as Naiad and Thebe, are likely remnants of earlier moons or formed in the debris disk that emerged after Triton's capture. Their proximity to Neptune and relatively stable orbits suggest they may have originated in a post-Triton environment. Overall, the capture of Triton marked a pivotal moment in Neptune's moon system history. This event likely caused Neptune's early moons to be ejected or destroyed and initiated a restructuring of its satellite system. The diverse and often eccentric orbits of Neptune's moons provide important insights into the early chaotic processes of the solar system, with Neptune's large moons offering valuable clues into the dynamics of planetary capture and evolution. The Oort cloud is a mysterious, distant area in our solar system, filled with icy objects that are too far away to see directly. Scientists have never actually observed it, but they believe it exists based on the paths of certain long-period comets that come from all different directions, not just the flat plane where the planets orbit. These comets take a long time to circle the Sun, which is why scientists think they are coming from a region much farther out than we've explored so far. The idea of the Oort cloud was first suggested by a scientist named Jan Oort in 1950, and it's used to explain why some comets travel so far out into space before they loop back toward the inner solar system. Think of the Oort cloud as a giant icy reservoir of objects that is so far away it stretches all the way from just beyond Pluto out to about 100,000 times the distance from the Earth to the Sun. It's a spherical region that wraps around the Sun, full of icy rocks, dust and possibly comets, each one a few kilometers in size or maybe even bigger. These objects are loosely connected to the Sun by gravity, but not in the same way the planets are. They're so far out that they're cold and faint, and because they are so small, we can't see them with our telescopes. Instead, we detect their presence through the behavior of comets that come from this far region. These comets, like Comet Hale-Bopp, travel in a very unpredictable path, coming from high up or from random directions in space, which is what you'd expect if they were coming from the Oort cloud. Other comets, like the ones from the Kuiper belt, a region closer to the Sun, move differently and arrive in a more predictable way. Scientists believe that the Oort cloud is where long-period comets come from, and it's likely full of many icy objects just waiting to be discovered. Now, while we haven't directly seen the Oort cloud, we've spotted the comets that come from there. These comets appear out of nowhere and take a long time to make their way back toward the Sun. What's fascinating is that the Oort cloud seems to be a kind of icy time capsule from the early days of our solar system, made up of leftover material from when the planets were forming billions of years ago. Even though we can't see the cloud itself, we're still learning about it from the behavior of comets that pass through our neighborhood. The Oort cloud is divided into two main sections, the inner Oort cloud, which is shaped a bit like a disk, and the outer Oort cloud, which is more spherical. These regions are still a mystery, but they seem to hold objects that are loosely connected to the Sun, though they're influenced by forces like passing stars and the gravitational pull of nearby galaxies. That's why the objects in the Oort cloud sometimes get knocked out of their orbits and start traveling into the inner solar system, where they become comets. Scientists believe the Oort cloud is a result of the giant planets, like Jupiter and Saturn, moving around early in the solar system's history. As these planets shifted positions, they caused nearby objects in the outer solar system to move too. Some of those objects ended up in the Oort cloud, and others were pushed inward, becoming comets. Interestingly, the Oort cloud may also be the reason we sometimes see comets showing up unexpectedly. When something like the gravity from a passing star nudges one of these icy objects in the Oort cloud, it can send it hurtling toward the inner solar system. When this happens, it looks like a comet, with a bright tail and a glowing coma, the cloud of gas and dust around its core, as it heats up when it gets closer to the Sun. Even though we haven't been able to directly observe the Oort cloud, its influence is clear when we look at how comets behave. These comets often take millions of years to complete their orbits around the Sun, and they are a key part of understanding how the solar system was put together. They give us clues about the types of objects that were floating around in the early solar system before the planets fully formed. The Oort cloud, if it exists, is like a frozen relic from the past, holding the building blocks of the solar system that haven't changed much in billions of years. Beyond just being a fascinating source of comets, the Oort cloud holds a deeper importance in our understanding of the solar system. Some scientists think the Oort cloud could be responsible for bringing water and organic materials to Earth during its early years. This could have played a role in kickstarting life on our planet. It's a bit like how some scientists theorize that water, comets and asteroids delivered water to Earth when the planet was still young. If the Oort cloud holds even more ancient remnants, it could help explain how life was able to emerge. So while the Oort cloud itself is still hidden from view, the study of comets and the behavior of objects coming from the outer reaches of the solar system gives us important clues. These objects are like messages from the past, revealing the conditions and materials that existed when the planets were forming. And as our technology improves, who knows what other secrets the Oort cloud might be hiding. The Oort cloud is a fascinating and mysterious region of space that, even though we can't directly see it, is full of clues about the solar system's early history. It's like a giant archive full of old icy objects, many of which have been there for billions of years. And thanks to the study of comets and other objects that pass through the inner solar system, we're slowly learning more about this distant part of our cosmic neighbourhood. In summary, while the Oort cloud hasn't been directly observed, its existence is inferred from the behaviour of long-period comets. These icy bodies, some of which may have originated in the Oort cloud, provide us with important clues about the solar system's early days and offer a glimpse into the conditions that led to the formation of the planets. As technology improves and new missions are launched, scientists hope to learn even more about this fascinating region and what it can tell us about the history of the solar system and the origins of life on Earth. The Oort cloud is a theoretical region far beyond Pluto, believed to be the source of long-period comets. These comets have large elliptical orbits that take them far from the Sun, and they don't return frequently, which suggests they originally formed far out in the solar system. Over time, some of these comets were disturbed by gravitational forces and sent on a path toward the Sun. The Oort cloud most likely formed during the early days of our solar system. When the giant planets formed, they interacted gravitationally with nearby icy planetesimals, pushing some of these objects out into the far reaches of space. While some of these objects escaped the solar system entirely, others were left loosely bound to the Sun and spread out over time, forming a distant shell. Galactic forces and nearby passing stars would have further disturbed these objects, reshaping their orbits and causing them to spread out in a spherical pattern. Even though the Oort cloud has never been directly observed, scientists have strong evidence supporting its existence. Numerical models and simulations show that early solar system dynamics, including the migration of the giant planets, could easily produce a cloud of icy objects at these extreme distances. The predicted number and distribution of comets from these models align well with what we see in the sky today. Sometimes when a nearby star or molecular cloud passes by, it can disturb the objects in the Oort cloud, causing a few to be sent on a path toward the Sun. This could explain occasional comet showers when many comets appear at once. Some researchers have even speculated that a distant companion star or planet could be influencing these comet showers, but so far no such object has been found. If the Oort cloud does exist, it forms the outermost boundary of the solar system in terms of gravitational influence. The farthest spacecraft, such as Voyager 1 and 2, are still tens of thousands of astronomical units, AU, away from the Oort cloud, and it would take many centuries for a spacecraft to reach it with current technology. This makes the Oort cloud one of the most distant and mysterious regions of our solar system. Interestingly, there's a possibility that similar clouds of icy debris, called exo-Oort clouds, exist around other stars. These exo-Oort clouds could be the source of comets in other planetary systems. Detecting them is a challenge, but scientists believe these clouds are likely common byproducts of planetary system formation. In summary, while the Oort cloud has never been directly observed, it remains the best explanation for the origin of long-period comets. It's inferred from the behaviour of these distant visitors to our solar system. The Oort cloud is a theoretical construct that continues to be supported by simulations, and it holds the key to understanding the origin and movement of comets. Even though it's far from the Sun and remains largely invisible, the Oort cloud is an important part of our solar system's history and a fascinating area for future study.